In this lesson, we're going to delve into the world of machine learning libraries. We will have a brief introduction to their utility, then we will look at libraries that are commonly applied in different domains, such as computer vision and natural language processing. This lesson will serve as an appetizer for some of the libraries we will use in this course. There will also be some dessert on the menu, where we will engage with some of these libraries and get a feel for their layout. So without further ado, let's take our first steps in our exploration of ML libraries. In this lesson, we will look at machine learning libraries and what spurred on the utility of these specialized libraries throughout various programming languages. We will also look at which machine learning libraries are used in computer vision tasks and natural language processing. For the last objective of this lesson, we will look at the functionality of scikit-learn, which is the library that we will primarily be using throughout this entire course. Now, let's examine how the need for ML libraries arose and what they're being used for. In 1949, a behavioral psychologist by the name of Donald Hebb published a book called Organizational Behavior. He looked at how learning affected neurons. He particularly noticed that neurons that are activated simultaneously, or where one neuron activates another, the chemical composition changed, forming what he called synaptic nodes, and increased communication between these neurons. This is a concept that was suggested by Freud 60 years earlier and neatly summarized by Carlos Schatz as neurons that fire together, wire together. Then, in 1950, Arthur Samuel created a program that could play chess. He was also the man responsible for coining the term machine learning in 1952. His program used alpha-beta pruning and the Minimix algorithm to assess the utility of each position on the board and make moves accordingly. Samuel built in functions to allow the program to learn as it plays, something that he then called rote learning. Then, in 1957, Frank Rosenblatt combined the concepts of Hebb and Samuel into a single model and called it the perceptron. The perceptron was originally designed as a machine. Perceptron software was installed into the machine called the Mark I perceptron. The machine was constructed for image recognition tasks, but failed to detect faces due to the linearity of the perceptron model. This caused the perceptron to be neglected for some time. It was revisited in the 1960s, and they realized that they could add more layers to the perceptron. These additional layers increased processing capacity, and revelations like the feed-forward network came into being. This is one of the networks that we discussed back in Lesson 3. Further applications such as backpropagation, which work on partial differentiation to analyze different conditions on nodes in the preceding layer, was also used in the new and improved perceptron. In a quick summary, the combination of the Hebb and Samuel model into the perceptron was formed. Of course, there was quite a few advancements in between that made the acceptance of neural networks more commonplace, but to prove the utility of them, it needed vigorous mathematical analysis in terms of statistical evaluation, particularly important in terms of validation, calculus, and linear algebra, especially with scalar and vector fields. Also, computations like partial differentiation needed for backpropagation is also performed with these two domains. And then also probability. Probability is important for measuring uncertainty and error. This is of increasing importance as the data sizes increase. The need for evaluation at a large scale led to the rise of machine learning libraries. We are very good at big picture thinking, but we need something to crunch the numbers for us, evident by how we use programs to do our matrix manipulations, or our parallel path coordinates, or all of those things are now automated. The need for these mathematical evaluations is evident by the emergence of the Theano programming language, which was one of the first models that provided effective evaluation in terms of mathematical operations, especially like matrix manipulations. The combination of evaluation and algorithms that constitute neural networks were also developed. We started to realize that we don't need one program to do the one or the other, but they can be combined. Library usages vary dependent on the task you are looking for, but in essence, they all perform some of the core functionalities, such as scientific computing. Libraries such as NumPy, SciPy, or MATLAB are all examples of this. Libraries are also used for signal and image preprocessing, such as early computer vision tasks when we convert pixel data. It is also used for matrix operations and evaluation. Although not just constrained to these mathematical operations, they are the operations that are most commonly encountered. Libraries are also concerned with optimization. This includes optimization of model parameters, compile time, and distribution. And libraries are also concerned with graphing, such as computational graphs and visualization of the process graphs. As we've seen, this is critically important in the setup of any model throughout lesson 4. Okay, so let's get starting with some of the commonly used libraries when it comes to computer vision libraries. Remember, libraries are not restricted to the domains we are discussing them in, but when they are mentioned, they are most commonly associated with this field. One of the very first libraries we will look at is TensorFlow, one of the most used libraries in computer vision and neural network tasks. TensorFlow is an open source platform, meaning that it has various contributors. TensorFlow is also a multi-platform API, which means that it can integrate with many of the most commonly used programming languages, such as Python, C++, and Java. By the way, TensorFlow was originally written in the C++ language. The reason why it's used for computer vision is because TensorFlow is a program that works very well with neural networks, especially constructing convolutional neural networks, or CNNs, that we've previously discussed. This is one of the best ways to deal with computer vision tasks currently. TensorFlow might seem like a strange and silly name, but it actually has a very descriptive name if you break it down. The flow in TensorFlow can be seen as a computational graph that illustrates the transformations that occur throughout the model creation process, something that TensorFlow allows us to see at runtime. Take, for instance, two datasets, X and Y. We can perform some transformation on the dataset to the denoted N format. In this transformation, we are simply taking a sample from the whole population. A represents our sampling function. We can then perform further transformations or make predictions on the transformed data and observe the effect it might have had. Remember, the hat notation represents our predictions. In our schematic, B represents the function that is used to create predictions on the data. Ideally, function f is the function we want to learn, but instead we end up with a learned f hat function. Each of these steps can be considered a node performing different functions. Dividing it further would make it just a layer in a schematic, or even just a node in a layer. Although our illustration does not represent a computational graph as produced in TensorFlow, the principle is very similar. This graph helped us to track the flow of our data. Without it, it would be easy to lose track of the different injection points. So to illustrate this more precisely, if we express our data transformation steps as layers, with different transformations as nodes, we can construct different interacting layers, containing nodes that perform a multitude of functions. Furthermore, we can establish how these nodes and layers interact, providing better clarity to the underlying process. If, for instance, you have determined exactly how you want two layers or nodes to interact, TensorFlow provides a computational graph that demonstrates how interactions have been constructed. If there is anything you are not satisfied with, you can do a debugging of sorts at runtime visually, saving loads of time in the model creation process and debugging process. Okay, so we can head on over to TensorFlow. If you want to follow along or check it out later, you can head over to tensorflow.org. Okay, so on install, we can go to install. We can see here we have our pip install. We have GPU support for TensorFlow. TensorFlow, one of the things that I really like about TensorFlow is that it has great tutorials, especially in Google Colab. Google Colab is actually something that we will be utilizing in Module 2 when we create our regressor and our classifier. It allows you to have real-time compiling printouts that's really intuitive to follow, which I really enjoy. You guys can also head over to Learn, where they have great guides for tasks such as pre-processing and model deployment. It actually has a very nice looking grid that lays out which language is able to perform which task, from load and pre-processing data to deployment. It has it for JavaScript, and if you want to write edge devices for iOS, Apple, Android, it has all the integration, and it's really intuitive to follow, which I really do like. And then finally, you can head over to resources. This is actually a very good tool because it can give you data sets to follow along with. A lot of the time, the data sets that they allow you to utilize is actually what the tutorials are based on. So it can give you just a really good understanding. Over here, you can see the data sets and the Google research data sets. So really do check them out if you have some time. Then it also, under resources, gives you a drop down of different applications. So if you go to libraries and extensions, same as you'll see with PyTorch, where we look at FastAI. This is also the libraries that are integrated with TensorFlow, which is really neat and interesting. There's really a lot to go around, and these libraries are just constantly being added. There's just constantly being more and more developed, which is really promising. You can head on over to LearnML, where they really have great courses to get you started with deep networks and building your own models, all the way, as you can see, from beginner all the way to expert, which is a great tool that they allow you to utilize. They even have a whole section dedicated to responsible AI, our topic we discussed in lesson 4, which is really great. They cover things like model fairness, model interpretability, and how to actually apply it practically and how it can add value within companies. It takes you through to the dropdown on constructing and preparing data, building and training, evaluating, deploying and monitoring, monitoring is actually really important, because your model might work great on deployment testing, but afterwards, as the data fluctuates and you get different data sets to work with, your model might not work as well. So it's of critical importance to evaluate it, and it's really cool that they give a guide on how to do that. So if you guys ever have some time, go check them out. Unfortunately, we won't be using them in this course, but perhaps that's something we'll change in the future, and we can have a TensorFlow dedicated course. Now for the tensor part of TensorFlow, which we mentioned back in lesson 1. Simply put, a tensor is a container with numbers. If we were to think of a gyroscope, the operations that occur to keep each ring of the gyroscope in alignment is what a tensor would represent. TensorFlow works extremely well with tensor operations. When TensorFlow is integrated with Python, the tensors are represented as objects, and the nodes represent the operations. Aspects of TensorFlow, such as high-level APIs that allow for easy integration, makes TensorFlow a tool in many developers' toolkit. TensorFlow allows for less hassle in creating and training of models that can easily be run on the cloud. This creates more robust models that are better suited for enterprise application. as the model will be less prone to erroneous operations. The intelligible and malleable architecture of TensorFlow makes it possible for research application without a creation period of 6 months before you can start with your research project, leading to quicker publications and novel discoveries. OpenCV is quite a popular library in terms of vision tasks, especially in live data analysis. OpenCV is an open source platform available to anyone, and like TensorFlow, OpenCV is a cross-platform library that integrates with various programming languages. OpenCV is particularly useful when it comes to real-time vision tasks, like identifying faces in real time. OpenCV is used for a lot more, of course, but primarily in vision domain, it is used for image processing, such as the processing of pixel data, video analysis, like 4K video aperture application, especially now during COVID, where the adoption of online classrooms have become more prevalent. Delivering a smoother and integrated experience for the student has become of critical concern, and something that OpenCV could possibly assist with. Feature detection is another application of OpenCV. This feature detection might include detection of features while driving, perhaps, or it could be of the identification of features within a dataset. Machine learning has been another application, once again for feature extraction and working with image data. Object detection has been primarily used in driving tasks, but it is also used as identifiers like object identifiers, something we will be doing when we create our clothing item identifier. PyTorch is a common used library in the construction specifically of neural networks. PyTorch is an imperative programming language similar to Python, and it's also implemented within Python. One of the benefits when working with Python is the strong support it offers for your GPU. As we saw in the demo with TensorFlow, which only integrates for NVIDIA GPUs, well, it doesn't exclusively integrate for NVIDIA GPUs, but NVIDIA GPUs are preferred. PyTorch allows for more scalability in terms of GPU support. And it also allows for tensors, which is tensor processing units, to be integrated. The PyTorch language is also very similar to how NumPy would function, which is a scientific language within Python. What makes PyTorch such a great library, like we already saw, we have tensor operations, but this is one of many matrices that are commonly used. Different circumstances might need an identity matrix to effectively represent a certain feature space, or you might need a Hermitian matrix, which might be better suited when working with a complex conjugate, or you might need to work with a determinant. If we need to understand how two spaces interact, finding the determinant of a matrix might be a better option. These more specific operations is exactly what PyTorch caters for. Whether you need an identity matrix, a complex conjugate, or a determinant, PyTorch allows for this flexibility. Of course, like we said, most libraries contain a multitude of applications. Like PyTorch is often used in NLP applications, but there are more specialized NLP libraries, and PyTorch is commonly used in neural networks and computer vision tasks. So here's our tutorial on PyTorch for everyone. I'm simply using this library because I think it's rich in resources, but it also has quite an intuitive layout. So you can play around and really see the general concept of libraries, and it also actually links quite well with TextAttack, which is discussed later in the lesson. So over here, you can see at Get Started, we have install options. PyTorch is primarily Python, and we will also be using the Conda and pip environment. This is actually one of the reasons why we will be using PyCharm, because it allows for interchangeability between these two. If you head over onto ecosystems, it shows all the different integrations with PyTorch. One of my favorites is actually FastAI, which has quite a few pre-trained models. Just to give you guys a quick illustration of what I mean with text attack when we get there, about adapting models like the recurrent neural network or the convolutional neural network that we've seen in previous lessons. If you head over to text and models, you can see this is the QRNN and also the long short term memory that we talked about in the previous lesson. These are all adapted models that are better suited to language related tasks. And then also you can head over to the documents. These are the documents that specifically look at applications in, be it audio or text, vision, which can be quite beneficial if you're looking for specific resources. And then also, PyTorch has a rich plethora of tutorials helping you to understand the functionalities of all there is, from text, as you can see, reinforcement learning, all the way up to parallel and distributed training, really making PyTorch a beneficial tool in my opinion, although I haven't used it all that much, something that I should look at changing. The name Keras is almost synonymous with compiling of neural networks, and is one of the libraries we will be using throughout this course. Keras is a high-level neural network library. High-level meaning it is relatively simple to construct. Keras also allows for dynamic computational graphs. This means that we can see the graphs on runtime as the model compiles and not at the very end of model compilation. Keras is an open source library. It is also a differential programming language. Essentially, automatic differentiation evaluation is what Keras allows for. Thus, every step in the model is validated and evaluated before being progressed to the second part. Keras is also built on top of TensorFlow 2.0, and it can be plugged and played into many libraries such as scikit-learn. Keras mitigates the problems that TensorFlow has with GPU support by allowing for GPU clusters. This allows many GPUs to connect together. Remember, this might sound familiar to cluster computing that we mentioned in lesson 2. Clearly, these fields all take from each other's subtopics and integrate them into their own application. Keras also has various tutorials on Google Colab. Actually, Keras is one of the libraries we will be utilizing throughout this entire course. We will be using it to create our neural network, whether it's creating dense input or output layers, and we will also use Keras in creating our clothing identifier. This is definitely going to be an exciting library that we're going to be using throughout. Now we progress to libraries that are often utilized when it comes to natural language processing. Our first library we will be discussing is none other than spaCy, our go-to NLP library for this course. spaCy is an open source platform, like various others mentioned before. spaCy was also written in Python and Cython. spaCy also utilizes neural networks to both optimize and increase model performance when working with language. Now, I'm just going to introduce a few spaCy functionalities, which might be conceptually a bit hard to grasp, but don't worry, they will be covered in depth later in lesson 8, if I am not mistaken. So, just to give a quick overview of some of the functionalities in a language library. One of the first applications is TF-IDF vectorizers, or term frequency inverse document frequency vectorizers. This method essentially assesses the importance of a word and is something that spaCy is aptly suited to perform. Named entity recognition is another functionality of spaCy, which is primarily concerned with extracting key elements from text. Another application is part of speech tagging. Part of speech focuses on mapping words to their parts of speech. Then we also have tokenization. Tokenization is something that is often applied in cybersecurity, but also in language. But in language, it looks at splitting text into different phrases. It also looks at splitting up spaces. This is actually where the name spaCy comes from, as it looks at the tokenization, which is the small spaces between words. Most scientific libraries in Python end in Y, such as NumPy or SciPy. Thus, they concatenated those two together and formed spaCy. But tokenization is also a task that it performs. We will be using spaCy throughout this course, both in our fake news identifier and when we use feature extraction in our NMF recommender. spaCy is a very good tool, often integrated with scikit-learn. So this is the last tutorial we'll be covering on the libraries, and just to kind of give you guys a flow on how it would look like, what I've found normally that your natural language process libraries aren't as visually interactive as you would have with PyTorch or Python. The exception to that rule is spaCy. This is probably one of the most user-friendly, interactive natural language processing platforms, where your NLTK is a little bit more open source, if you will. It's more documentation that instructs you on how to use it, where here it's an user interactive instruction. But I really think it's a cool library. Here they have pip and conda. Conda is what we'll be using to build our model in PyCharm, and spaCy can be easily imported into it. You can choose your configuration on models you want to choose, and it gives you instructions on it. It even has some of the best pre-trained language models in different languages, from Chinese all the way to Spanish, which makes spaCy really great. And that's why spaCy is so often applied, is because it has such a wide range of already pre-trained language models that can be used. So here you can go and you can choose which language you want to use, and they tell you which keywords to use to import it and what you primarily want to use it for. One of the things that I also like about spaCy, if you go back to usage, you can choose whether you're going to use a GPU or a CPUs on your installation. And it has CUDA support, which is primarily for NVIDIA, but it is one of the few libraries in language terms that allows that customization within installation, where you don't actually have to go into the program and do too much configuration within that. I hope it's been intuitive. I'm sorry we couldn't go through more applications, but here you guys can also see it has tokenizers, named entity recognition, some of the things we'll talk about a little bit later. It has your word embedding, so it's very intuitive to follow around. And that's something I think you'll find too often within language libraries. So I think this is a very good place to start if you guys want to get to learn language processing a little bit better. Natural Language Toolkit is a library used for NLP-related tasks, as the name obviously suggests. NLTK is apt at string processing, and it is also often utilized for parts of speech tagging, as with spaCy. It is also very adept at sentiment analysis. So, if you want to concatenate sentiment analysis with the functionalities of spaCy, that is also a viable option. NLTK is often used in education and research, as it learns fundamentals and a steps-wise progress. It also contains various pre-trained models. In order to use a language model, it needs to be fitted to your vocabulary. This is exactly what NLTK allows us to have in a pre-trained format. The downfall with NLTK is its steep learning curve, with difficult syntax and quite an abstract way of compiling code together. which makes it not very accepted within industrial applications. The NLP library that I quite enjoy is TextBlob, although my fondness might be linked to the fact that the logo represents the Mandelbrot set. When we deal with a complex plane, we have a set of real and imaginary numbers that can be represented in a function. As we iterate over these functions, some of them might loop back on themselves, resulting in the animated image you see. This is but a nutshell representation of the Mandelbrot set, and understanding its true complexities is something I still struggle with. In terms of TextBlob, there are primarily three metrics to determine textual relationships, namely polarity, which determine how related two words are to one another. This is done by converting text to vector representations. Subjectivity, which is the mathematical evaluation that expresses opinion or emotion, and also intensity. Intensity checks if a word modifies the meaning of the text. For instance, love and like might be equivalent statements in most cases, but when said to a person, it alters the meaning of the text. TextBlob is particularly beneficial when it comes to sentiment analysis. TextBlob works with strings. In Python, objects are the strings. TextBlob is also adept with parts of speech tagging and sentiment analysis, as we mentioned before. Because of these properties, TextBlob is particularly well suited for finding interrelating facts. Cue the Mandelbrot animation. Interestingly, one of the properties of TextBlob is that it works better with unstructured data. This is like image and audio data. The last NLP library we will glance at is TextAttack, not because it will be applied, but it is really interesting. If we look back at the GAN network we covered in the previous lesson, this is how TextAttack essentially functions. It finds words discrepancies in a model, and then it tries to replicate an ambiguous meaning behind it. TextAttack is primarily a Python framework, and it works very similar to the GAN network as we described with a discriminator and the latent variable that is introduced. Remember we said this is typically used with computer vision tasks. This is an example of an adaptation on the GAN network. For instance, if you take I love England and you compare it to I love Turkey, these two words should have the same meaning. But because of the negative correlation that is often in media text of Turkey, the sentiment behind those two similar phrases do not come back as the same. This is something that TextAttack primarily addresses, and this increases model robustness. It also helps with data augmentation, creating better scenarios on which to evaluate certain phrases and vocabulary content. This is particularly well at handling word ambiguities, like we mentioned with the England and Turkey augmentation. Okay, now finally for our final topic, we're going to look at scikit-learn, the library that we're going to use throughout this course. Previous libraries were primarily focused on neural networks. Scikit is more orientated towards machine learning tasks. Thus, it integrates well with supervised and unsupervised learning tasks. Apart from that, scikit-learn integrates well with neural network libraries such as Keras and TensorFlow, but it can also integrate with Python and various others. We will be using scikit-learn in a practical sense, but scikit-learn allows us to work with pre-processing of models. It helps us to work with model selection, choosing different models and how it affects it, such as the k-nearest neighbor or principal component analysis. And it also allows us to evaluate our models, whether it's using mean squared errors or cross entropy. There's a lot of different ways we can evaluate it, and scikit caters for specifically those variations. Scikit-learn integrates well with other APIs, like we mentioned with TensorFlow and Python, but it can also be integrated with various others, which can be a limiting factor in most of the other machine learning libraries. It also allows to be injected into neural networks, allowing for hyperparameters within neural networks to be adjusted directly by scikit-learn, providing more granularity in the tasks that you work with. Unfortunately, scikit-learn does not have large-scale support. So as our datasets increase and we work with more and more information, it can become hard to process all of that information, which is a limiting factor from scikit-learn. Nonetheless, we will be using scikit-learn when we create our fake news classifier. We will also integrate it with spaCy. We will be working with it in our clothing identifier, which will also be integrated with Keras. We will use scikit exclusively when we build our regression model and our classification model. It will also be imported when we build our NMF recommender. Congratulations everyone for completing lesson 5. I look forward to seeing you all in lesson 6. We'll be handling data and pre-processing. This lesson